Okay, welcome to another fabulous video with Calculus 3, directional derivatives and gradients. What is a directional derivative? Suppose you're standing on a hillside. You want to determine the hill's incline, that's its slope, towards the z-axis, okay? So if your hill is represented by a function of two variables, you already know how to determine the slopes in two different directions. You know the slope in the positive x-axis direction, because that's dz dx, the partial derivative of z with respect to x, which can also be denoted with the subscript notation. And the slope of your hill in the positive y-axis direction is dz dy, which you can also denote fy. What if you want the slope somewhere else? Like, what if you want to go in between the x and y axes? So here's you standing on the mountain with your skis, and you're like, hey, I don't want to go in the positive x direction. I don't want to go in the positive y direction. Those are nice, but maybe I want to go diagonally in between those two axes. What's the slope going that direction? Now you're ready. Now today we're going to find the slope in any direction you want. And this is a new type of derivative. It is called the directional derivative. I'm going to derive it. And it's an interesting derivation because you're going to look at it as rise over run, which you kind of did look at a derivative that way in Calc 1, where you took the difference of the y variables or coordinates to get your rise. And the run was the difference of the x coordinates if you were doing, say, a secant line. We're going to do something similar. We're going to take the rise being the difference in altitudes, so the difference of the z coordinates of 2 points. But the run is going to be the difference between the 2 points down in the xy plane. So it's going to be kind of interesting how we do the analog here in 3D. So let's say you've got a surface, and so they're just showing you this blue surface here. You can think of that as your mountain surface. And let's talk about a point P with coordinates x naught, y naught, that's down here in the xy plane, because that's one of the domain points. And then you have a vector u that's going to be a unit vector that's also in the xy plane, that's going to point you in the direction that you'd like to take your slope. So they're not showing you here, so I'll show it. Let's say I'll draw u in standard position. Down here in the xy plane is u. So let's point it like, in the direction of, say, a diagonal. And, you can always give your u in the xy plane its components. It'll be cos theta, sine theta, where theta is the angle that the little vector u makes with a positive x-axis. So the slope, when we reduce this problem to 2D, where we're going to do rise over run, is we're going to intersect the surface with a vertical plane. See, this diagram I have here, this yellow vertical plane, you can think of it as a big knife chopping into your surface vertically, and the intersection of that vertical knife with your surface gives a curve here. This curve right here, we're going to call it curve C. Wow, that's kind of cool. And that knife, if you will, it makes a trace of this line down here in the xy plane, which is going to be parallel to your direction vector, u, parallel to u. So your vertical plane is passing through the point P and parallel to you. Now, how do you find the slope? What's this got to do with slope? Well, the point P has up here in heaven on the surface, the associated order triple has the same coordinates as point P for x and y, and then the z coordinate on here in the surface is f evaluated at x naught, y naught, okay? And the slope right there is going to be the slope of the curve at that point. So if I draw a tangent line to that curve, oh boy, that is a terrible looking line. Let me use a different color. I'm going to try to draw a straight line here. That's a tangent line. So here's what our claim. the slope of the surface at the point, and we'll call this point on the surface P prime, because it's kind of associated with P there, P prime, which coordinates x naught, y naught, f evaluated at x naught, y naught for its z coordinate, in the direction of the vector u is defined as I'm having trouble writing, the slope of the curve C at that point. That's the claim. So what we're going to do is this line L, if you were to give it parametric equations, it would have x, y, and z, parametric equations. Z would be 0 because that line is in the xy plane. So its z parametric equation would be 0. The x and y, well, it goes through this point with coordinates x naught, y naught, and then the direction vector is u. So then you'd have cos theta t, and then sine theta t be the other two terms for the other parametric equations, respectively. So now what? Well, if we pick a different point on this line, Q, and we look at the distance between P and Q, and that's going to be our run. So we're trying to do rise over run here. So the distance between P and Q on that line is D, and we're just going to use the distance formula in 2D. You know, x minus x naught squared. Q is just going to have arbitrary, this Q just has arbitrary x, y as coordinates, plus y minus y naught squared. But we already know something here. X, since it's on the line, if we substitute that parametric equation for x, and then we do a similar thing where we substitute y, which is equal to y naught plus sine theta t, some stuff is going to cancel. So my distance formula, when I do these cancellations, is, or substitutions and then cancellations, it's going to look like this. These x naughts cancel, these y naughts cancel. And so what am I really squaring here? I've got cos squared theta t squared plus sine squared theta t squared. And you know from working with trig stuff, if you factor out a common factor of t squared, the other factor is sine squared theta plus sine squared theta plus cos squared. That's 1. And so this is just square root of t squared, which is going to be the absolute value of t. So there's your run. So now what? The slope of a secant line through P prime, which has coordinates x naught, y naught, f evaluated at x naught, y naught, and Q prime. Q prime is going to be a point directly above Q, on the surface and also on the curve right there with coordinates x, y, fxy. And what does a secant line look like? Like, what is a secant line? Well, if I just, it's something that you wish were the tangent line, but it isn't. And you did something similar to that in a Calc 1 class. So the secant line through those 2 points, I really want to get the tangent line to my point P naught. So this is what I really want, because the real slope is this tangent line. But a good approximation to that tangent line would be the secant line, which goes through these 2 points like this. That's the secant line. And it's almost the same as my tangent line, like good enough for government work, close enough. So it's going to be rise over run, and it's going to be the difference between the x coordinates. And the run was that t absolute value of, because you want it to be positive. So now what? Well, we really wish this were the slope of the tangent line, and this is where you take a limit. Although the last little piece here before I take the limit is, remember, the x and the y have to live on that line. So the more accurate is x naught plus cos theta t for the x, and you substitute y naught, those parametric equations, and then you go like this. And now you take the limit as that run goes to 0. So the official, we're done with the derivation. The theorem is a limit definition. Really? Yeah. So here it is. So the limit definition. You got f, it's a function of two variables. You got a unit vector that lives in the xy plane. The components are cos theta, sine theta. That's a unit vector. It's pointing you in the direction that you want this directional derivative. And so the directional derivative of f in the direction of u is denoted big D, subscript u, f. And is given by big D, subscript u, f, x, y, is what? It's a limit as t goes to 0 of this huge difference quotient I just did, f evaluated, and they replace the x naught, y naughts now with just x. They get more generic. There's theta t, comma, y plus sine theta t minus fxy all over t. Okay. Good news, we're not going to use the limit definition. Oh, why'd you do it? Well, for your edification. Now, of course, provided the limit exists, because if it doesn't, and it might not, it's not always does your limit exist when you're doing derivatives, right? So, because it is a challenge to find directional derivatives using a limit definition, we're not gonna. Yay! We're gonna use an easier way. Yay! What's the easier way? Here it is. Theorem. This is the one you're gonna use, so put stars by it in your notes. Directional derivative for a function of two variables. You got a function f of two variables, x and y, and let u be a unit vector with components cos theta, sine theta, pointing you in the direction that you want your slope. Your directional derivative of f is duf. Know this notation. The duf xy is going to be the following. You take the first partial of f with respect to x, xy, and you multiply that with the cos theta, the first component of your unit vector, plus you take the first partial of f with respect to y, xy, because it is a function of x and y, and multiply that by the other component of your unit vector. Yay! And before we do some examples with this, let's kind of do a little bit of fun and play with it. Fact, there are infinitely many directional derivatives when you're on a surface, well, when it corresponding to a single point. Why? Because when you're standing on a surface, let's say you're a skier, you can look in infinity different directions. You can spin yourself around 360 and point your eyeballs looking at any one of infinity directions and get the slope in that direction. Okay. That's going to be important for you to kind of get. Now, what if theta were equal to 0 in this theorem that I just did? What does that mean? It means that your u, your vector that's pointing you in the direction that you want the slope, is exactly pointing in the positive x-axis direction. So in other words, u would look like, cos 0 sine 0, which is 1, 0. So it's pointing in the positive x direction. So then what would your directional derivative end up being? Well, you'd have your fx, and you're multiplying it by cos 0, which is just 1, plus your fy multiplied by sine of 0 degrees, but that's 0, so you just would end up with fx. But does that make sense? Sure, because when your direction is the positive x-axis, you better get fx, because that is the slope. in the positive x direction. So this formula works. And similarly, what if your theta is pi halves or 90 degrees? So then your little direction vector is, cos pi halves, comma sine pi halves, and cos of pi halves is 0 and sine of pi halves is 1. 0, 1 is pointing in the positive y-axis direction. So what would your directional derivative be if your little direction vector was the vector 0, 1? Would be fx times the cos of pi halves, 0, plus fy times sine of pi halves, which is 1, and that's just going to give you fy. And of course, that's what you want. That should be the slope in the positive y-axis direction. So this formula here really does the trick. Okay? Now, we'll do an easy example and then something a little trickier, and then we're going to have you try one. So here's a nice function of two variables, 4 minus x squared minus 4th y squared. And at the point 1, 2, they want us to find a directional derivative in this particular direction. So they're giving us the direction, and it is a unit vector, thankfully. And so, and you can even check this. I just want to put fact, this is a unit vector. Well, how do you know? Well, if you really don't believe me, go ahead and use the magnitude formula, square root of the sum of the squares, and you'll see this magnitude is 1. The unit vector. So good. Well, why is that so important? Because one thing that students don't get, because some of them don't really listen to lecture, is this directional derivative formula in this theorem will not work unless you get that this has to be a unit vector. And if you do something other than a unit vector, I don't even give you any partial credit. You'll see. So how do I get the directional derivative? Well, first let's go get those partials. Fx is the partial with respect to x here. What do I got here? I got minus 2x, and I think that's it. Ooh, that's easy. How about the other partial with respect to y? I get, that's 0. Let's say, okay, minus 1, 4. I think that's going to be minus a half y. Okay, fine. So the directional derivative in the direction of u, fxy, is going to be using the formula fx xy times cos theta plus fy xy sine theta. But they already gave me like the cos and the sine, right? So they gave me, everything. So I'm going to have negative 2x times cos pi thirds minus, or I'll put plus, and I'll put minus a half y sine of pi thirds. And now at the point when x is 1 and y is 2, now I'm just going to do some substitution. Negative 2, x is 1. Cos of pi thirds, what is that? Isn't that a half? Plus, and then here I have negative a half times y, but they're giving me a y coordinate of 2. Sine of pi thirds, ooh, I think is square root of 3 halves. And then clean this mess up. Okay, we can do some reducing. More reducing over here. I get negative 1 minus square root of 3 halves. That's the exact answer. And that's approximately negative 1.866. Okay, so there's the exact and the approximate answer. Okay, and I'm done with example 1. So what did we learn? We learned that we can find the slope in a different direction. And this is the direction where I'm making an angle of pi thirds with a positive x-axis. And for this particular problem, the slope is slightly negative, which means I could ski down that hill because it is negative, which means I'm going downhill, not uphill. So I could conceivably ski in that direction. Pretty cool, huh? Okay, caution. Be sure that the direction is a unit vector. Because if it's not, then you need to unitize it. So I'm going to do example 2, and then we'll have you try one. So here is a new example. We have a z, a function of two variables here, x squared sine 2y. And we want to find the directional derivative at this point. in the direction of this vector. So my question to you is this direction vector a unit vector? What do you think?
No.
No. Good. So what does that mean? You got to go unitize it. So better unitize it right now. Like, don't wait. Like, oh, I'll do it later. No, you need to do it now, immediately. Okay. So in order to unitize it, I'm going to have to go get that all-important magnitude, you know. Oh my goodness, this is going to be a nice magnitude. That doesn't always happen, but 5. And so my unit vector pointing in the direction of where I want to find this directional derivative is going to be, after I distribute my scalar, 3/5, -4/5. Now I have a unit vector to go worry about. Now, here's something that I need to say at this moment, which is a big student mistake. And in my view, it's not a silly mistake. It's a mistake that the student never got the material at all. Listen up, because you don't want this to be you, where you just didn't get it, even though you think you got it. In the formula, it says, boy, did I make a mess over here, huh? Fx times cos theta, Fy times sine theta. What if I don't have the theta? Do I have to now go get it? Oh, man, no, you don't. Look, once you have a unit vector in hand, it's understood that that very first component, this is for a 2D vector, of course, not 3D, that first component is the cos theta. Like, you don't have to go, oh, I need to go arc cos something to go get my my theta. No. You just use that first component and multiply it with your fx, and you use that second component. So what am I trying to say here, in case you're still confused? This 3/5 is a cos theta, and you don't have to go get the theta. Like, don't bother. If you waste valuable time right now on a quiz or exam going to find theta, and let's say you did get the right answer, I'm going to just take points away for wasting time. Well, that's not fair. I got the right answer. In my book, getting the right answer, while important, is not the be all. It's process also. And if you go off, down, some wrong path that doesn't help out the whole situation and you're wasting valuable time, I dock your points for that. Don't waste time. This is the sine theta. Okay, now what? Let's go get the partials, fx and fy. I'm still working on example 2. All right, what is the partial of f with respect to x? We're going to treat y as a constant, and that means that sine of 2y is just a constant. Yeah, it just goes along for the ride. It's just a multiple. So you're going to multiply the sine 2y with the derivative of x squared with respect to x. And so there's our first partial with respect to x, 2x times sine of 2y. Getting the other partial, you're going to hold x constant now and take the derivative with respect to y. X squared is just a constant multiple. Copy it down and multiply it with the derivative of sine 2y with respect to y. And that's going to be 2 times cos of 2y using the chain rule. I'll put the 2 in front, make it look pretty. Now, you want to evaluate these partials at the point given. So now you're going to go, what is fx at the point with coordinates 1, 2, right? And just substitution. Is that what I got here? No, pi halves. 1 pi half. I don't know why I had 2 there. Something. I'm looking at another problem. So I have 2 times 1 sine of pi halves. Okay, sine of pi halves is what? 1? Okay. So this is going to be just 2. Fine. What is the other partial evaluated at the point that they want us to do? 1 pi halves. So you're just going to use substitution, except here I'm going to have cos of 2 times pi halves. Be careful. This isn't cosine of pi halves. That would be 0. This is not 0. After canceling the 2's, does anybody know what cos of pi is?
-1.
So I have 2 times 1 times -1. This is going to be -2. Okay, fine. I'm almost ready to be finished. The directional derivative, big D, subscript U, F, at the point 1 pi halves is fx.
Excuse me, Professor.
Yeah.
For the F subscript X, wouldn't it be sine pi as well?
And then it would be 0.
Oh, you're right. I wasn't even looking. Thank you. My bad. I was testing you. Yeah, that's a 2 in there, huh? 2 times pi halves. So that would be sine of pi. And that wouldn't be a 2, would it? That would give me 2 times 0. 0. Oh, bummer, man. Okay, well, that's fine. So now when I get my big old directional derivative, I'm going to have fx at the point, that's a big fat 0, as you guys just pointed out, thank you, times the x component of the unit vector, 3/5, but 0 times anything is 0, so why bother? But I just want to make a point. Plus the fy evaluated at the point, that was -2, times the y component of my little unit vector, and that's -4/5. And then what is my final answer? Well, I get a positive 8/5. Now notice that is a positive slope, which means I couldn't ski in that direction because it's going uphill a little bit. And so this is your final answer for example 2. And how about you guys try one? I'm going to give you a couple of hints because this one's a little bit hard for a couple of reasons, but I think it's good for you to get a little stretch on a Friday. So here is your function of 2 variables, and notice it is a quotient. So you might have to use the quotient rule when you find a partial. And that's a hint. They're giving you the point that they want you to find a directional derivative of. And here's the thing, in the direction of the point Q. So what's missing from this problem that we had in example 2? Example 2, they gave us a point, like they gave us here, but remember example 2, they gave us a direction vector. They didn't give us a direction vector for this one. That wasn't very nice, but you're going to get one. And so how are you going to get one? So step 1, this is a big hint for you, is your direction vector is going to be, and you probably already guessed it, PQ. You with me? You guys know how to form a vector given 2 points, right? Now, step 2, remember that in your directional derivatives, your direction vector has to be a unit vector, no exceptions. So your next step is you need to unitize that direction vector you just got. If you fail to unitize it, I don't care what you do in this problem, no credit. And then go get your partials and evaluate them at your point, and then put it all together and get your big old directional derivative, okay? So let's take a look here. You got your function. This is example 3. And they're giving you a point and they're giving you another point. They're giving you 2 points. And as we mentioned, they didn't give us a direction vector. So we have to go get it. So hopefully you did that as your step 1. That's the PQ. And you guys know terminal minus initial, and I get the components -2, -1. Next up, you have to unitize it, because otherwise you can't use it in the directional derivative formula. The directional derivative formula requires a unit vector, period, no exceptions. So you're going to go get the magnitude to help you. And I get square root of 5. So then my unit vector pointing in the direction that I'd like to get this directional derivative, that directional derivative is just a slope, is going to be this cute little unit vector with components -2 over square root of 5 and -1 over square root of 5. Okay, great. Now, the next thing we need to do is we need to go get our partials. So if this function is what we're going to work with, and I'm going to call it z because it's the same. Let's go z. If I'm going to get zx, which is the same as fx, I need the quotient rule. And the reason why is because I'm working with a quotient. X is appearing in the numerator and the denominator. So I'll call the numerator f and the denominator g. And back when you took the quotient rule in Calc 1, hopefully this formula looks familiar to you. It's classic. F prime g minus g prime f all over g squared. All of the derivatives that you see there, the f prime and the g prime, you will be taking them with respect to x when you're trying to get this partial with respect to x. So let's do it. What is the derivative of the numerator x with respect to x? 1. We did that. Now multiply that by g, parentheses matter, x plus y, minus, now let's do the g prime. What is the derivative of x plus y with respect to x? 1 times f, but that's x. And then you're going to do all over g getting squared. Now, the numerator can be simplified further because after you have your 1's, x plus y minus x, you can cancel the x's. So your fx is this quotient. Okay, now you want to evaluate that guy at a point because you want to get a pure number. So which point should you evaluate him at? P or Q, or does it matter? Yes, it matters. And it has to be at P. Q is only given to you in order to give you a direction. It's not the point at which you actually want that slope. So P is the point you're going to evaluate at. So you're going to evaluate at the point 1, 0. Oh, wait a minute. What does that mean? What are we going to get here? Isn't that a big fat 0? Nice. Okay, now let's go get fy. Now you could use the quotient rule because the function is still a quotient, but I'm going to rewrite the function as a product. So I'm going to do a rewrite because I don't have to use the quotient rule because the x in the numerator is really just a constant when I'm differentiating with respect to y. So I rewrite it as x plus y to the -1. And then when I take this derivative of x plus y to the -1, x is a constant multiple, copy it down. Using the chain rule on x plus y to the -1, I get -1, x plus y to the -2 times the derivative of x plus y with respect to y. But that's just 1. And then rewrite this using positive exponents because it's easier for you to plug stuff in. And now when you evaluate this partial at the point 1, 0, I don't get 0 this time, I get -1. Okay, fine. Now you're ready to finish this problem out. Because your directional derivative, your du, is going at the point 1, 0, is going to be, fx at the point 1, 0, times your first component of your little unit vector, plus fy evaluated to the point 1, 0 times -1 over square root of 5. So this was a big fat 0. This was -1 times -1 over square root of 5. And your final answer is 1 over square root of 5. So did anybody get that? I know at least one group got it because when I walked into the room, they had it. Anybody else get this? You can do a show of hands or a checkbox or something.
I got it.
Okay, we got Aaron got it. Okay. Now, folks, one thing that needs to be clear, this could even be a true-false question. True or false? The directional derivative is a scalar. True or false?
True.
True.
Yes, it's true. So what do I mean by that? If I get somebody giving me a vector as their final answer for a directional derivative, like they, start using angular brackets or i's and j's, I'm going to go, what the heck are you doing? No bueno. Okay, so quick check. Is the directional derivative a vector or scalar? Scalar. Okay. Now, what is a gradient? Let's do gradients. I want to start the little gradient here. I think we have to back up a little bit because I skipped it. So it's going to seem like I'm doing a brand new topic. Like, hey, we just got done with directional derivatives. Why the heck are we talking about gradients? Does that have anything to do with anything? And the answer is yes, it does. Be patient. Okay. So what is a gradient? We've already discussed that there are infinitely many directional derivatives at the point on a surface. Yes, that's true. So like if you look at some surface, any surface, let's just look at this one here, you know, and you pick a point on there, any point, I don't care where, you know, pick a point like, hey, I'm right here and I'm standing here and I'm going to go skiing. You could spin around and look in infinity different directions and talk about infinity slopes, you know, depending on where you want to go head on your ski trip. Okay. So here's the question. In a lot of applications, you might want to know which direction you should go if you wanted to go in the maximum slope possible or in the direction that the function increases most rapidly. And this is called the direction of steepest ascent. It's basically the maximum slope you're going to get. Okay? So if you want to put in parentheses your max slope possible at that point, that's basically what it is. I'm not kidding you. Okay? So how do you get that? Like you have infinity directions to go ahead. Which way is going to give you that max slope of all? And that's given to you by the gradient vector. What's the gradient vector? We're going to go over it now. Congratulations, here it is. The definition of gradient. Really, yeah. Let f be a function of two variables x and y, such that the first partials exist. And the gradient of f is denoted del f of xy. That is an upside down triangle, and it's when you read it, say del. Well, what is del fy, fxy? Del fxy, that's the gradient of f, is a vector. And here's the cool beans part of it. The components are simply the partial derivatives for that function. That's the gradient. That's it. That's a gradient. So in example 4, let's find a gradient for this cute little function, fxy equals y ln x plus xy squared. And we'll find the gradient at the point 1, 2. Let's go get the partials first. Fx, you're going to take the derivative with respect to x. So hold y constant. So the first term will be y times the derivative of ln of x with respect to x, which is 1 over x, plus the derivative of xy squared with respect to x is just y squared. The other first partial with respect to y, so the derivative of y times ln x with respect to y, ln x, plus the derivative of xy squared with respect to y is 2xy. And now let's get the gradient. The generic gradient for any point xy, which is just going to be a vector containing the partials. So the first component of this vector is y over x plus y squared, comma. Other component is ln x plus 2xy. That's the gradient at any point. But they want the gradient specifically at the point 1, 2. Fine, we're going to just evaluate the partials at the point 1, 2. And you're just going to use direct substitution. Let's see, 2 over 1 plus 2 squared for the first component, ln of 1 plus 2 times 1 times 2. I get, this weird vector. So this gradient is the vector, what? ln1 is 0. That's nice. I get 6, 4, and I'm done. That's your gradient. What does that mean? That means if you're on the mountain and you're standing when the coordinates x and y are 1, 2, if you point yourself in this direction, the direction 6, 4, you'll be pointing yourself in the direction of the steepest ascent on that mountaintop. So you couldn't go skiing in that direction because this is going to be a positive result. You would actually ski in the opposite direction to get your most steep descent. We'll see that in a moment. So there's your gradient. We just did a problem involving gradient. So is the gradient, whoa, too far, stop. Is the gradient a vector or a scalar?
Vector.
Yeah, vector. So let's finish out this problem here. And then, did I skip something here? No. Hang on a second. Really? Okay. We're going to wrap this up, sort of a grand finale today. And this is cool. I want you to get that the gradient is a vector, true. And the directional derivative is not a vector. It's a scalar. But I want you to look at the directional derivative theorem one more time, because I'm going to give you an alternate version of it. It's not different. It's just going to be the same thing, but in a more cool beans way. So go back to when I defined what the directional derivative was, way back here. Remember? Look at this formula. It's got fx times a cosine plus fy times a sine. Yeah, so what? Doesn't this have a flavor to you of a dot product? Something times something plus something times something else? Yeah?
Yeah.
It's got that dot product flavor? It is! It is a dot product. Folks, I am not kidding you. The directional derivative is a dot product. Well, okay, but it's a dot product of what two vectors? We're getting there. We're almost there. You're so close. Oh, this is exciting. This is a big day for you because you're going to see the alternative form for the directional derivative. Here it is. This is the one I memorized because it makes more sense to me. You still got your f. It's still a function of two variables, x and y, blah, blah, blah. Fine. Yep. And you're going to have your direction vector for what direction you want your slope going in. And it's still going to be this 2D vector, cos theta, sine theta. And it's got to be a unit vector. That is key. That's still got to be true. Okay. No exceptions. The directional derivative of f in the direction of u is denoted and is given by d subscript u f xy. And it's going to be the gradient del fxy dot product with your direction vector. Yep. Because remember, your gradient is simply a vector with the partials as components. Remember? We just studied the gradient 5 seconds ago. So it's going to give you the fx times the cos plus the fy times the sine. So the directional derivative really is a dot product. Cool, huh? Let's do one example, getting another directional derivative, only this time we're going to use the gradient to get it. Okay, so we're going to go through an intermediate step. Okay, so how do you get the gradient of this function? Well, the gradient del f xy is simply a vector that contains the partials as its components. Okay, easy peasy. Let's go get these partials. All right, this is an easy one. Hey, the partial of 3x squared minus 2y squared with respect to x is 6x. And the partial of the function with respect to y is negative 4y. And now go get the del f at the point. So which point should I get the del f, the gradient, at? Should I evaluate him at the negative 3, 4, 0? Or should I evaluate him at the 0, 1? Or does it matter?
Negative 3/4, 0.
Good. Yeah, you do it at the first point. The second point is just to give you a direction. So you're going to evaluate this gradient at the point -3/4, 0, and just use direct substitution, easy peasy. And well, the second component is 0. This is going to reduce to, what the heck is it going to reduce to? I think it's going to reduce to what, -9/2? Okay, save that for later. Now what? I got to go get the direction vector. So let's do PQ, where P is the -3/4, 0, and Q is the 0, 1. Okay, terminal minus initial. Terminal minus initial. So I get my direction is 3/4, 1. Now unitize it. If you don't unitize it, you're going to blow it. Oh no, let's go get the magnitude. Oh man, this magnitude is going to involve fractions. Bummer. Oh well, you know, it is what it is. Okay, what the heck is 9/16 plus 1? Well, 1 is the same as 16/16. I'll go with that. And then if I add 9/16 with 16/16, I get 25/16 under the radical. But then if I use a law of radicals, cool beans, and break it up into a quotient of radicals, I end up with 5/4. So now what? My unit vector is going to be my vector divided by the magnitude. And if you don't mind, I'm going to skip a step. Dividing by 5/4 is the same as multiplying by his reciprocal, isn't it? So let's do that. And then if I distribute that 4/5 and reduce, my unit vector, I unitized them, is 3/5, 4/5. Okay, fine. Almost done. Now my directional derivative of the function at the point -3/4, 0 is going to be the dot product of the gradient with my unit vector. So remember, my gradient was -9/2, 0, and I'm going to take his dot product with the unit vector 3/5, 4/5, and you guys know how to do dot products, right? Yeah, this is old news. And then after I multiply 0 times anything is 0, I get -27/10. And that's my final answer. My directional derivative at that point given was -27/10. And that's the slope. Directional derivative is a slope. So congratulations, you now know what a directional derivative is, as well as a gradient. And you know the way to find a directional derivative using the gradient. Pretty cool, huh? And that concludes today's lecture.